On October 5, 1999, a driver passed a red signal outside Paddington station and entered a section of track occupied by an oncoming express traveling at 130 kilometers per hour. 31 people died. The subsequent inquiry found that the same signal had been passed at danger 8 times in the previous 6 years. The technology that would have stopped the train automatically, regardless of what the driver did, had been available for a decade. A cost-benefit calculation had determined it wasn't worth installing. 5 years after that calculation was made, Ladbroke Grove happened. Here's what that technology does, why it was rejected, and why it's still not fully deployed. The collision geometry of a railway has no equivalent in any other transport system. A car that encounters an obstacle can swerve. A ship can alter course over minutes or hours. An aircraft has 3 dimensions to maneuver in. A train has 1 dimension, the track beneath it, and no ability to deviate from it under any circumstances. 2 trains on the same line, moving toward each other, will collide with mathematical certainty from the moment both enter the same section of track. There is no reaction time that helps. There is no steering input that matters. At 100 kilometers per hour, a fully loaded passenger train requires over 1,200 meters to stop from emergency brake application. By the time a driver sees an oncoming train at that speed, the stopping distance required is already longer than the visible distance available. The only collision prevention that works happens before both trains enter the same section. Not during, not after. This insight is 170 years old. The block signaling system, dividing a railway line into discrete sections called blocks and permitting only one train to occupy any block at any time, was the railway industry's first systematic answer to the collision geometry problem. The concept is straightforward. The execution requires a system that knows with absolute certainty whether any given block is occupied or empty before authorizing a second train to enter it. Getting that certainty wrong in either direction has consequences. Authorizing entry into an occupied block causes a collision. Incorrectly reporting a block as occupied when it is empty paralyzes the network. The system needs to be right every time in both directions, in all weather conditions, across thousands of track sections simultaneously. The solution arrived in 1872 and has not been fundamentally replaced since. A track circuit feeds a low-voltage electrical current continuously into one rail of each block section. The return path runs through the opposite rail. At the boundaries between adjacent blocks, insulated rail joints break the circuit electrically, preventing current from flowing between sections. A relay at the signal controlling entry to each block sits in the circuit path. When the block is empty and the circuit is complete, current flows through the relay, holding it energized, and the signal displays green. When a train enters the block, its steel axles, conducting metal bridging both rails simultaneously, short-circuit the current between the 2 rails. The current bypasses the relay. The relay de-energizes. The signal drops to red. The train is its own sensor. Its weight, its axles, its presence on the track. All of it feeds directly into the signaling system without any active component on the train itself, without any radio communication, without any GPS position report. The track knows the train is there because the train is completing a circuit the track is always trying to run. Here is the distinction that matters. The track circuit does not detect the presence of a train. It detects the absence of an open circuit. Those are related conditions, but they are not identical. And the gap between them is where people die. A fractured rail severs the electrical circuit at the point of fracture. Current cannot flow through broken metal any more than it can flow through air. From the track circuit's perspective, a section of track with a completely fractured rail is electrically indistinguishable from a section of track that is empty and in perfect condition. Both present an open circuit. Both cause the relay to energize. Both cause the signal to display green. The system that was designed to prevent a train from entering an occupied block will clear the signal for a train entering a block containing a broken rail, a derailed vehicle, debris across the running line, or any other condition that has severed the electrical continuity of the track, because all of those conditions look identical to an empty, functional block. The track circuit has been the foundational layer of railway collision prevention for 150 years. Every train control system built since, in every country, on every high-speed line, still depends on it at its base. And every one of them inherited this blind spot. The broken rail failure mode is the physics problem. The human failure mode is different and statistically more significant. A driver who passes a red signal removes the track circuit's protection entirely. The track circuit correctly shows an occupied block and drops the signal to red. The signal correctly displays red. The driver passes it anyway, from distraction, fatigue, misreading, or a moment of inattention that occupies perhaps 2 seconds, and produces consequences that occupy the rest of the inquiry's report. This event has a formal designation in railway operations. Signal passed at danger, SPAD. The track circuit has no mechanism for SPAD. It shows the signal. It cannot enforce the signal. The entire collision prevention architecture built on block signaling operates on one assumption that is embedded so deeply in the system's design that it was never explicitly stated as an assumption, that drivers obey red signals. When that assumption fails, the system has no response. The track circuit tells the network exactly where every train is. It has no mechanism, none, for what happens when a driver sees a red signal and drives through it anyway. The track circuit solves the occupation problem. It cannot solve the human problem. That gap was understood within the railway industry for decades before anything was built to close it. The engineering concept behind automatic train protection, a system that monitors a train's approach to a red signal, calculates whether braking has begun at the required distance, and applies the brakes automatically if the required deceleration is not detected, existed in various forms across European railway systems from the 1970s onward. The principle is direct. Remove the driver from the final layer of collision prevention. If the driver acts correctly, the system does nothing. If the driver does not act, the system acts instead. The train stops whether the driver chooses to stop it or not. The driver cannot override it. That is the point. British Rail commissioned a study of ATP installation across the UK network following the Clapham Junction crash in 1988, which killed 35 people and was caused by a wiring fault rather than a SPAD, but which focused political and public attention on railway safety investment. The study reported an estimated installation cost of £750 million across the network. The Treasury's regulatory cost-benefit framework evaluated safety investments against a defined value per statistical life threshold. At £750 million against the projected SPAD casualty rate, ATP failed to meet the threshold. The investment was not approved. The system was not installed. The calculation was not made in bad faith. It used the standard methodology applied to every public safety investment in British infrastructure at the time. It was also wrong, not because the arithmetic was incorrect, but because cost-benefit analysis applied to safety systems with catastrophic failure modes cannot account for the specific crash that will eventually occur, only for the statistical distribution of crashes that have occurred previously. The methodology was designed for the past. Ladbroke Grove was in the future. On October 5, 1999, a Thames Trains driver passed signal SN109 at Paddington at danger and entered the Ladbroke Grove junction on the wrong line. A First Great Western HST was approaching on the same line at 130 km per hour. The collision killed 31 people and injured over 400. The subsequent public inquiry, led by Lord Cullen, found that signal SN109 had been passed at danger 8 times in the 6 years preceding the crash. Its sighting distance was poor. Drivers approaching it at speed had fewer than 4 seconds of visibility before passing the signal face. The infrastructure created a condition where a SPAD was predictable. The absence of ATP created a condition where a predictable SPAD was fatal. Had ATP been installed, the system would have detected that the Thames train service was approaching SN109 without beginning the required braking sequence. It would have applied the brakes automatically. The train would have stopped before the junction. 31 people would not have died. The inquiry's conclusion on this point was unambiguous. The ATP that was available. The cost-benefit calculation said it wasn't worth installing. 5 years after that calculation was made, Ladbroke Grove happened. The inquiry recommended ATP. The industry began installing it. The system that could have prevented 31 deaths was approved for deployment after those 31 deaths made the calculation change. The European Train Control System, ETCS, represents the current standard for collision prevention on new and upgraded lines across Europe and beyond. In where ATP enforces a binary stop or go decision at each signal, ETCS provides continuous speed supervision across the entire line. Trackside beacons transmit line speed limits, gradient data, signal aspects, and stopping point locations to an onboard computer. The computer calculates a dynamic braking curve, the maximum permitted speed at every point along the route given current conditions and the stopping distance available. If the train's actual speed exceeds the permitted speed profile at any point, the system intervenes. The driver cannot suppress the intervention. Speed authority is not granted by a signal the driver passes. It is transmitted continuously to the cab and enforced continuously by the onboard unit. ETCS Level 2 removes line-side signals entirely. The authority to proceed is transmitted directly to the cab display. The driver has no signal to pass at danger because there is no signal on the line side to pass. The SPAD failure mode is architecturally eliminated, not mitigated, eliminated. ETCS Level 3 removes the track circuit. Train position is reported directly by the onboard unit rather than detected by the infrastructure. Level 3 has not been deployed at scale on any mainline network anywhere in the world. The reason is the broken rail problem identified 150 years ago. The track circuit that Level 3 eliminates to achieve fully autonomous train separation is also the system that detects fractured rails, debris on the track, and stalled vehicles through the circuit brake mechanism. Removing the track circuit to achieve full automation simultaneously removes the only passive infrastructure failure detection the network possesses. And no technology currently certified for mainline railway use replicates that detection function without the track circuit. Level 3 solves the human problem and creates a new version of the physics problem. The railway has never found a single technology that simultaneously provides occupation detection, broken rail detection, overspeed prevention, and driver override. Every network operating today uses a layered combination of technologies: track circuits at the base, ATP or ETCS above it, driver advisory systems above that, because no single layer is sufficient and the consequences of any layer's failure are measured in lives. The system is not designed, it is accumulated. Each layer exists because a specific crash exposed the gap between what the previous layer could prevent and what it could not. The Clapham Junction added ATP to the agenda. Ladbroke Grove moved it from the agenda to the network. Every protection added to the railway in the last 150 years was added in response to a crash that the existing protection failed to prevent. That is not an indictment of the engineers who built the system. It is a description of how safety engineering actually works when the cost of a wrong answer is 31 people at Ladbroke Grove, or 35 at Clapham, or the specific number attached to the next crash that reveals the next gap. The track circuit is still running current through the rail beneath every train operating today. The relay is still dropping when the axles bridge the circuit. The signal is still showing red when the block is occupied. The system from 1872 is still the foundation. The everything built above it is the answer to the question it could not answer alone.